start. All right. So hello, everyone. Thank you for joining today's tea talk. Today we have Katherine Zucker visiting us from the space from STSI, where she is a Hubble Fellow and she studies ISM and structure in the Milky Way. And today she's going to be telling us about her work on the solar neighborhood. So Katherine, you can share your screen, make your slides full screen and take it away.
Yep, okay. Thank you, Dana, for the introduction, and thank you guys for having me. Today I'm going to be talking to you about our ongoing work to try to reconstruct the star formation history of our solar neighborhood. And specifically, I'm going to argue that we can explain the origin of all nearby star formation as being due to the expansion of the local bubble. And so before I start, I just want to thank all my wonderful co-authors. You can see them down here, my collaborators, particularly Alyssa Goodman and Joao Alves, who have been pretty instrumental in this work. Okay. So this is sort of the picture that we've been forming. So this is essentially all nearby star forming regions within 200 parsecs. So you can see them listed here by name. So Taurus, Chameleon, Corona Australis. Anyone who studies nearby star formation has known that these regions have been well studied for about 100 years or so. And so we find that every nearby star forming region, they lie on the surface of the local bubble. And so the local bubble as a entity has been known about for about 50 years. So its existence was first posited in around the 1970s. And so we've known about the local bubble as a region of lower density with respect to its surrounding medium, being more highly ionized and also hotter. But what we didn't know, and what I'm going to talk about today, is the relationship between the local bubble and nearby star formation. Okay, so I just want to sort of give you the local bubble and nearby star formation in the context of the galaxy. So this is a sort of a cartoon model of the Milky Way from Robert Hertz at IPAC. And we're going to sort of zoom in to the solar neighborhood. So the sun's shown here in yellow. And then in purple, that is the model for the local bubble that we're going to be using in this study from Pelgrims et al. I'll talk about that a little bit later. And then these sort of green spiny things, that's the location of all nearby star forming regions within 200 parsecs of the sun. And then sort of people always ask, well, if sort of this local bubble is so close, why didn't we figure out sort of where all these regions were situated with respect to the bubble surface before? And the answer is that there's no way to know this unless you have a very high spatial model, a 3D spatial model of the local ISM. So if you sort of zoom in to the Earth and you sort of look out at the star forming region on the sky, of course, the local bubble surface is all around us because we're inside of it. And so you really need a very precise model of where all these star forming regions are, where the surface of the bubble is, and also how the gas is moving as a function of time. And so that's what I'll be talking about today. The end of the story first. So the first key point of this story is that we can now reconstruct a high resolution 3D model in both space and time of nearby dense gas and young stars. And when we do this, when we reconstruct this model, we find that the local bubble is responsible for all nearby star formation. And so there's sort of three ingredients in this story. So all of the data that I'll be using today is actually all based on publicly available data. And so really a lot of the work that we've been doing has just sort of been piecing together independent lines of evidence in order to tell a story of nearby star formation. And so we need three ingredients to sort of reconstruct the local bubbles and nearby star formation's origin story. So the first is we need to know the 3D spatial distribution of dense star forming molecular gas. So we need to know the properties of the gas and also precisely where that dense star forming gas is located with respect to the sun. Then we need to know the 3D space motion of this dense gas, and we're going to use its young stars, the young stars that were born in these dense gas clouds as probes of its 3D space motion. And then finally, we need a model for the surface of the local bubble. And so I'm going to go through all three of these ingredients really quickly. So first we need a 3D spatial model of dense star forming molecular gas. And we're going to obtain this model via a technique called 3D dust mapping. So essentially 3D dust mapping uses the effect that dust has on stellar colors in order to map its 3D spatial distribution. So you can imagine that there's just a star in the Milky Way. We observe this star from photometric imaging. So we have 2D images of stellar colors. And so if this star was intrinsically green and there was no dust cloud between us and the star, that green star would appear green to us. But of course, that's not true. There are dust clouds all over the galaxy, and the light from that star will become reddened in proportion to the amount of dust column it passes through. And so an intrinsically green star will no longer appear intrinsically green. And so you can imagine, and you can see this very clearly in something like B68, this sort of reddening effects we all know and love on the outskirts of this cloud, where the stars on the outskirts of B68 appear more reddened than the background stars. And so you can imagine that we don't just have a single star, but we have billions of stars throughout our Milky Way, sort of scattered throughout this cloud in 3D and scattered throughout the galaxy in 3D. And so depending on where the stars are located with respect to the cloud, they'll become more or less reddened. And so of course, the situation is more complicated because stars have different intrinsic colors. But you can imagine that if you had a very advanced statistical pipeline, you could simultaneously infer the intrinsic colors of all these stars, where all these stars are located in the galaxy, and the 3D distribution of dust that produces the observed distribution of stellar colors on the plane of the sky. And so you can infer a cloud's distance from dust effect on stars. So if you know where something is in the sky, you know its distance, and you can build these 3D spatial maps of the ISM. And this situation actually improves exponentially overnight thanks to the launch of the Gaia mission. So you can actually do 3D dust mapping just using the colors of stars and nothing else, so just photometry. But if you have independent constraints on where these stars are located in the galaxy on their distances, the distance resolution of your corresponding resulting dust map improves by a factor of 5 essentially in a day. And so 3D dust mapping has experienced sort of a revolution in the past few years thanks to Gaia and thanks to these large photometric surveys. And so this is how we get the 3D spatial distribution of dense star-forming molecular gas. This is just an example of what a 3D dust map looks like. This is a 3D dust map from Greg Green et al. That I was involved in a few years ago. So this is actually a 3D dust map on much larger scales. So this is showing you the solar neighborhood out to about 2 kiloparsecs. And so the how much stuff there is corresponds to sort of the brown color that you see. And so we observe the sun's at the center here. And so we observe like these large scale features in the dust map. These are sort of linear structures. And so those are various spiral arms and spurs of the galaxy. One of them over here, Mike Kuhn actually led a paper on showing that the Sagittarius arm actually has a very high pitch angle. So you can ask me about that and then if you're curious. Okay. So a lot of the work I did during my early PhD has been focused on dust map, but on very large scales. So this is a top-down view of the same dust map you saw earlier. Out to 2 kiloparsecs. And so we're looking down on the disk from above as from a bird's eye view. And so we've done a lot of work on sort of classifying where these large scale features are. So the one I've highlighted right here, this is actually a part of the local arm of the galaxy, and we call it the Radcliffe Wave because we think the local arm that's nearest to the sun, the section of the local arm nearest to the sun, actually takes the form of a sort of a damped sine wave. But the idea is that we have a really good view of the large scale structure of the galaxy out to a few kiloparsecs. And so I'll come back to this later, but we have a sense of like supernova-driven feedback in the larger galactic environments. But for the purposes of this talk, I want to talk about efforts that were carried out by other groups that have actually focused on sort of zooming into the region just around the sun to produce even higher and higher resolution 3D dust maps. And so what I'm showing you in the middle panel is a 3D dust map from Leica, Glatzel, and Enslin in 2020. This was done by the Information Field Theory group at the Max Planck Institute for Astronomy. And what they did is they basically sacrificed the amount of the galaxy they can probe for increased spatial resolution nearby. And so they're using Gaussian processes in order to create a 3D dust map with 1 parsec resolution within a few hundred parsecs of the sun. And so you can actually zoom out down into individual clouds in the spiral arm, for instance, in this structure called the Radcliffe Wave. And you can actually analyze their detailed topologies and morphologies of the gas at 1 parsec distance resolution, which is really exciting. And so in about 2 years, we've gone from being able to look at distances of these clouds and sort of map their global distribution to being able to map their precise shapes and properties at 1 parsec resolution. And so we can now expand a very large dynamic range in spatial scale and actually in dust density as well. It's just a single cloud that we've looked at. So basically, what I've done is using this new map from Like It All 2020 is I spent 2021 essentially going through and classifying the detailed properties of all nearby star forming regions. So this is just a gallery of famous nearby star forming regions. And this is showing you their true 3D volume density distribution. So in true 3D XYZ space. And so basically every property that you would want to know about a molecular cloud, we've measured it in 3D. So we've measured, this is looking at their radial profiles and different tracers. So we measure the radial volume density profiles of these clouds, their masses, their sizes, all that stuff. But the takeaway is that we know lots of stuff about the clouds now at very high resolution. And we also, as a result, we also know precisely where they are with respect to the sun to about 1% distance uncertainty. And so we do now have a map of the 3D spatial distribution of dense star forming molecular gas. So that's ingredient number 1. So good, we have 1 ingredient. So the second ingredient in order to build this picture is that we have to have some understanding of the 3D space motion of the dense gas. And so how are we going to get that? So specifically what we're going to use is we're going to use the young stars that are forming in these clouds as a proxy for the motion of their parental gas clouds. And so you can see here, this is a young star cluster you can see in yellow here in the Perseus molecular cloud. And then this little vector is showing you how that star cluster is moving in true 3D space. And so basically for the star cluster, we have full 60 information. So we know from Gaia where it's located, and we also know from Gaia radial velocities and also proper motions, exactly how it's moving in three dimensions. And so this is a valid assumption using young stars to trace the motion of the parental gas, because young stars have not strayed too far from their birth sites. And also young stars share similar radial velocities to their parental gas clouds. And so we're going to use young star clusters as a probe of the motion of the dense gas. So it's just sort of a plot that sort of validates that assumption of, for young stars, the gas and the stars share very similar radial velocities. So this is a work from Josefa Großschädel in 2021. And she basically looked at along a nearby molecular cloud called Orion, the offset in radial velocity between the gas and the stars. This is just for different positions along the cloud. The blue shows the gas radial velocity, and then the yellow shows the stars. And so they're green within about 1 kilometer per second. And so basically what we're going to do is we're going to look at the 3D space motions of dense gas clouds on the surface of the local bubble, and we're going to see the expansion through their young stars. Okay, so second ingredient, 3D space motion of the dense gas. We're going to use this to constrain the expansion of the bubble, and we're going to do it using the dense gas of the young stars. And then finally, we need a model for the surface of the local bubble. And so there are many ways to trace the bubble. So you can trace it as an absence of material. You can trace it as a region that is devoid of neutral gas. So you can look at the ionization state of the gas in the bubble. But the model that we're using is based on Pelgrims et al. 2020. And that's based on the 3D dust map from Rosine Lalemant. And basically what they do is they look for, they integrate out from the sun. You can see in the bottom panel here. And they're looking at different sight lines out from the sun, which just are these different curves. And they're looking for sharp changes in the differential extinction. And so they're basically looking for the first boundary of any material that you reach as you look outwards from the sun. And so that's what this looks like in a top-down view. This is 3 different models, 3 different views of the local bubble from Vincent Pelgrim's. This is a top-down view. This is a side view, and this is another side view. And you can see in red here, this is what they're saying for the bubble boundary. So where they see any change in the dust distribution, very sharp changes. But one thing that I'll note is that we spent a lot of effort. We actually wrote a 30-page referee report trying to look at the boundary of the local bubble and all different tracers. And we found that they agree. So the different bubble tracers agree very well. And that in all cases, these star forming regions lie on the surface of the bubble, regardless of which bubble model that you're using. Okay, so we have our 3 ingredients. And so now I want to show you the picture that we built for the solar neighborhood. It's just an interactive figure. This is showing you the nearest 400 parsecs from the sun. So we're looking out down at the top down view. So I'm just going to turn some stuff off, just focus on the dust distribution. So this is a 3D dust map from Like et al. 2020, showing the gas distribution at 1 parsec spatial resolution. And then what I'm going to turn on right now are the positions of the star forming gas. So these little cloud skeletons, so everywhere you see a skeleton, you have young stars that are forming. And then I'm going to turn on the motion of the young clusters. So if I zoom down into these regions, you'll see that we have little arrows that are sort of coincident with these sort of grayish blobs that represent the gas clouds. And so we're actually looking at how the gas is moving over time. And specifically, the apex of the cone points in the direction of motion. And so what we're finding is that if we turn on the model for the local bubble, not only does every nearby star forming region within 200 parsecs of the sun lie on the surface of the local bubble, but if you actually look at the 3D space motions of the young clusters that are on the surface in these gas clouds, we find that in every case, they're oriented perpendicular to the bubble surface. And so the clear implication of the position and also the motion of the dense gas near the sun is that all of these star forming regions have been swept up to the expansion of the local bubble. And so we think this is evidence of supernova-driven star formation in action. And so I want to sort of zoom in now into sort of the detailed physical picture that we are proposing. But let me just turn off one more time so you can see the little star clusters a little bit better. So you can see in all cases, they're pointing outwards from the surface. Okay. So basically, if we know the present positions and motions of the clusters, we can actually trace them back in time and figure out where they were in the past in order to reconstruct the history of star formation in our solar neighborhood. And what we're proposing is that about 14 million years ago, powerful supernovae started exploding in clusters in what is now known as the SCO-SUN stellar association. And that triggered a shock wave. And that shock, behind that shock, you had the gas rapidly cool and become compressed. And you get dense gas being swept up on the surface of the local bubble. And so essentially, let me just play it one more time. The local bubble is expanding. You'll see it's sweeping up gas clouds. That gas collapses and forms young stars. And so this is why we see the observed spatial distribution and kinematics of dense gas near the sun. So on the left-hand side, we have the cartoon model, and on the right-hand side, we have the actual data. And so one thing you'll notice on the left-hand side, we have both the gas and the star clusters represented, but on the right-hand side, we only have these point sources, and those are just the motion of the star clusters that we're using to probe the motion of the gas. Okay, so basically what we do is we use the dynamical data on the young clusters in order to fit a model for the evolution of the local bubble as a function of time. And so the idea is that we can trace back the orbits of these young stellar clusters. And if we know their ages, we know when they're born, we have a position of when and where they were born in the galaxy. And if you assume that these clusters formed due to the expansion of the local bubble, that provides a constraint on the size of the local bubble as a function of time. And so what we do is we adopt an analytic expansion model from El-Badri et al. 2019. And that model assumes that the local bubble is entirely supernova driven. So we're neglecting any effects from radiation pressure or stellar winds. But basically our model fits for the time of the first explosion. We fit for the ambient density of the ISM when the first supernova went off. And then we also fit for the time interval between the supernova explosions. And so just to emphasize, it's the spherical shell expansion model. So it's a very simple model for how the bubbles evolved over time, but you can see as it expands, you see these little clusters that are forming on the surface. So I want to walk through that evolution in more detail. Okay, so this is just sort of the constraints that we're getting from the cluster data on the bubble's evolution. So as I said, we fit for these 3 parameters. And then when we do that fit, we get a couple plots of how the local bubble evolves over time. So the top panel shows the expansion velocity as a function of time. So negative 14 million years ago is when we say the bubble first started, the first supernova went off that created the local bubble. And then t=0 is the present day. And so we have the expansion velocity as a function of time. We have the shell radius as a function of time. And then we're also modeling the momentum injection per supernova as a function of time. And so here you see our model for the expansion of the local bubble as it evolves about 14 million years ago to the present day. And what's really exciting is we actually think we also know the clusters that hosted the supernova that powered the expansion of the local bubble. And so basically what we find is that about 15 and 16 million years ago, there were these two massive clusters in the SCO-SEN stellar association that were formed about 10 parsecs apart. So they were probably formed in the same molecular cloud. And so previous studies had argued that these two clusters could have powered the expansion of the local bubble, but the stellar trajectories actually placed them outside the bubble when they formed. But we had actually revisited those clusters and revisited the trace effects, and we find that they're actually near the center of the clusters, center of the bubble where it would have started forming. And so we're providing even stronger evidence that this is the progenitor population. So I'll talk about that in a second. But basically, we have these two massive clusters that are forming, and then shortly after they're formed, supernovas start going off. And so basically, the supernova in these two massive clusters drive the expansion of the bubble. And then the bubble will keep expanding over time. And as it expands, you'll find these clusters forming on the surface. And so basically, these little paths show trajectories of young stellar clusters. But if there's no dot at the end of the path, that means the cluster hasn't been born yet. So every time a dot appears, that means that a cluster is formed on the surface of the local bubble. And so we start seeing star formation about 10 million years ago. And we actually see sequential star formation in some regions where we have like an earlier, like a later star formation and an earlier star formation epoch. So like some stars will form 10 million years ago and then a few million years ago in the same region. Anywho, the bubble continues to expand, it expands and expands. More stars form on its surface about 6 million years ago. Keeps expanding, even more stars form on its surface, keeps expanding, even more stars form about 1 or 2 million years ago. And then we hop from our spherical shell expansion model to the current distribution of dense molecular gas enveloping the local bubble with all the motion of the gas sort of pointing perpendicular to its surface. Okay, so I mentioned that we think we know what the progenitor population for the local bubble is. So specifically, there are these two clusters in the SCO-SEN stellar association called UCL and LCC. So in case you're interested, that stands for Upper Centaurus Lupus and Lower Centaurus Crux. And basically, this is their present positions. They're just inside the inner boundary of the bubble in the present day. But if you trace them back, they met at the same location, so they probably formed in the same molecular cloud. And previous work has looked at the sort of population synthesis modeling of these two clusters. And through this population synthesis modeling, they've argued that these two supernova have produced about, these two clusters have produced about 14 to 20 supernova over their lifetimes, over the past 15 or so million years. And then if we actually look at how much momentum needed to be injected by supernova in order to power the expansion of the bubble, we actually find that we need about 15 supernovae. And so our momentum analysis agrees with the population synthesis modeling, which is really good to see. But essentially what we do is we can look at the swept up mass in the local bubble. So we think there's about 1.4 million solar masses of gas that's been swept up on its surface. And then based on the cluster modeling, we find an expansion velocity of about 7 kilometers per second. And so we have the total momentum of the shell. And then if you divide that by the momentum injected on average by each supernovae, you get about an average of 15 supernovae needed to power the expansion. But there's a wide range. So anywhere from about 8 to 30 supernovae is sort of the range of possibilities that we get. Okay, so what's the sun doing? So it's a pretty interesting story. So how did the sun wind up the local bubble? So we actually traced the motion of the sun with respect to the bubble expansion model over time. And we find that the sun was about 300 parsecs away when the bubble first started forming. So you can see here, sun sort of moving towards the local bubble. And then it actually crosses over. We're arguing that it entered the local bubble about 5 million years ago. And so it's just by chance that the sun sits near the center of the local bubble. So we're near the center in the present day. But what's really interesting is that if you look at sort of what effect the local bubble has had on Earth, So what does the sun's time in the bubble mean for Earth? We find that our sort of timeline for when the sun entered the local bubble is consistent with the timeline for when supernova iron deposits would have been deposited into the Earth's crust. So basically, these supernova produce iron-60 in their explosions, and the iron-60 has a known half-life about 2.6 million years. And so other studies, specifically by Dieter Breitschwert et al. And Wallner et al. 2016, have looked at how much of an influx in iron-60 there was as a function of the age of the deposits. And this is what that's showing. This is showing sediment deposit of iron-60 produced in these supernovae as a function of time. And they specifically find, Wallner et al. 2016, that there is an influx between about 1 and 4 million years ago. And that's consistent with when we think the sun entered the local bubble. And so essentially this iron-60 gets incorporated into dust grains and sort of then gets deposited into the solar system and then into the deep sea crust. And people have analyzed this to find the ages of the deposits. So that's, I think, just a super interesting fact. The one thing we can't explain is why there's this sort of older iron-60 also deposited in the deep sea sediment. But if you want to ask me about that during the question and answer, I'm happy to explain where we think that came from. Okay, so what are the takeaways? So first, we find that in the present day, almost every single nearby young star lies on the surface of the local bubble. And in doing so, we're arguing that we can explain how nearby star formation began. So we're arguing that these results present very robust observational evidence, what we call 6D space, so 3 dimensions of space and 3 dimensions of velocity, that supernova can sweep up gas into dense clouds that ultimately form new stars. So of course, this has been a long-held theory for decades, and we see it all the time in simulations. But this is, to our knowledge, a pretty systematic attempt to sort of produce the same dimensionality that we can see in simulations. And then finally, sun's luck, the fact that the sun is centered inside the bubble suggests that these bubbles must be pervasive across the galaxy. And so we've actually been working on trying to piece together where all these neighboring bubbles are. And we think that this is quite common in the solar neighborhood and that many, many clouds lie as surfaces on the edge of superbubbles. Okay, so it's just a brief ode to analytic theory and numerical simulations. So you can see sort of the supernova-driven star formation scenario going all the way back to McKee and Oestreicher 1977. This is their paper where they argue for a 3-phase ISM, where there's the existence of this very hot tenuous phase powered by supernovae. You can see sort of like these large superbubbles, 200 parsecs in extent, similar to the local bubble, and then these neutral cloudlets forming on the surface. And this is just a more modern view from Inetsuka 2015. Which argues that they can explain both the cloud mass function and the star formation efficiency via molecular clouds being formed via superbubble collisions. And so these GMCs are forming as these superbubbles collide on all different scales. And then this is just one simulation from Kim and Oestreicher 2017 that's showing the multi-phase ISM evolution over 44 million years. And so the key panel is this top panel where you see this massive cluster forming in this dense molecular cloud. It sort of creates a cavity in the ISM. As gas is swept up in the shell, you see these dense cloudlets that are forming on the surface and creating new generations of stars. And so we're getting about 1 parsec spatial resolution, about 1 or 2 kilometer per second velocity resolution, and about a mega year time resolution. And so I think we can really start doing some more systematic comparisons with simulations. Okay, so what's next? What are we planning to do in the future? So the first thing we want to do is we want to find more of these bubbles in a systematic way. So the question is, how do we search for other bubbles? And so some of this is easy because a lot of these bubbles are very famous, like the local bubble. They've been studied for a very long time, but some of the bubbles are going to be much less obvious. And so you basically have to take a multi-wavelength approach where you look at the bubbles as cavities in 3D, but correlate them with tracers of supernova activity in 2D. So the other question is exactly how these bubbles interact with each other. So we actually know right now that there's a newly discovered superbubble in the solar neighborhood called the Perseus-Taurus Superbubble. You can see it in green right here. And it contains this cloud called Perseus on its far side and Taurus on its near side. And we actually found that this Taurus molecular cloud in red It actually lies at the intersection between these two superbubbles. So it's perfectly sandwiched in between these two superbubbles. And it actually displays like a sheet-like morphology because it's being compressed by successive shocks, which is really interesting. And so essentially understanding how sort of interaction of multiple superbubbles affects cloud and star formation is something that we're actively hoping to pursue in the future by finding more bubbles in the solar neighborhood. So the other question we want to look into as well is the relationship between superbubbles and galactic structure. So I promised I would go back to sort of our understanding of large scale structure in the Milky Way. And what we actually know locally is that the local bubble actually lies in between two major spiral features of the galaxy. So on the left-hand side of the bubble, this is called the Radcliffe Wave. It's a part of the local arm of the galaxy and extends about 3 kiloparsecs in length. And then on the right-hand side, this is called the split, and it's a spur or a spur between the local arm and the Sagittarius Carina arm. And so if you actually look at how the local bubble is affecting the gas on very large scales, you can actually see these arc-like morphologies being sort of crafted into the arms. So you can sort of see how these bubbles interact with their larger scale galactic environment. So understanding the interplay between galactic dynamics and superbubble evolution is also something that we're actively looking into. And then finally, we want to know whether observations can better constrain supernova feedback's effect on galaxy evolution. And so for that, we will definitely need some collaboration with theorists. And so I'm hoping to speak more with Phil Hopkins Group in the future about that. And that's all I have for you today. If you have any questions, I'm happy to answer them. So thanks for your attention.
Great. Thank you, Katherine. Let me see if I can pull up participants. So please raise your hand if you have any questions. So Lynn, I think you're the first to raise your hand. Go ahead.
Sure, thanks. Thank you for the talk. I'm glad to have the opportunity to ask you more questions in person soon. So that'll be fun. I have a lot.
Yep.
I guess one specific thing would be, does this model allow you to explain the age dispersions that we see in these different star forming regions? So the specific examples that you mentioned, the SCO-SEN complex on the one side and the Taurus Perseus region on the other. And each of these, it's not just, I think your model needs to explain not just the recently compressed gas within the past 1 to 2 million years that's forming stars, but the extended star formation that's ongoing with ages up to 10 and 15 or more years. And so in the case of UCL and LCC, right, that's those clusters at the origins of the supernovae. So we've been, I guess, walking our way down the IMF with these successive supernovae. But on the other side, how is it that your model produces all of the star formation history, right? As I said, it's not just the compressed molecular gas that we're recently seeing, but 10 million years of star formation have been going on in that direction. Yeah.
So that's a great question. And so one thing that we've done, let me pull over. And so I'll put a disclaimer on this that we'll be able to do this much better and test this in much more detail in Gaia DR3. And so in about 3 months, we'll get 4 times more radial velocity. But when we fit for the model of the superbubbles expansion, we're actually simultaneously fitting the expansion of, so for instance, in Taurus, so what you're talking about, just a discrete example, in Taurus, we see a population that's 6 million years old, and then we see a population that's 1 or 2 million years old. And in Ophiuchus, we see a population that's 10 million years old, and another one that's 1 million years old. And so we actually fit all of that when we're modeling the expansion of the bubble. So the idea is that, let me just pull this up.
So just some asymmetry in the density of the expansion?
Yeah, so basically, we're assuming a spherical shell expansion model, but basically what we're accounting for is that, so when a star cluster that's 10 million years old forms, that provides a constraint on where the bubble must have been in the past. And so basically we're trying to figure out whether a very simple expansion model can simultaneously explain the formation closer in at earlier times of the clusters, and then also the clusters that are forming at later times. And so if you actually look at this in action, so like, let me show you what this looks like. So you can see here that there are these 2 clusters that form in Ophiuchus on the surface. So when it's much smaller, So these are clusters that are about 10 million years old. This is Upper SCO, actually, the Upper SCO cluster. And then, so that provides a constraint in the past. And then as it keeps expanding, you'll see in the future a little bit more, I think it's about 2 million years ago, you'll see another cluster that's formed at later times. And so we're actually fitting the multiple epochs of star formation. That's actually the only way that we can model the expansion of the bubble. And so I think as we get more and more data, we'll be able to do this in much greater detail, but we do actually explicitly account for sequential star formation in individual regions. I don't know if that answers your question. Yeah.
Yeah. So it sounds like it's not a predictive model. It's a, includes the parameters in different pieces of 4pi to get the reality out. Okay. Now I understand. Thank you.
Yeah. So it's the latter. So we're not predicting anything. We just want to see whether the numbers make sense. So whether like we know a certain number of supernovae powered the expansion of this bubble, it's swept up a certain amount. Like we know the age of the bubble. Can we build a very simple model for its evolution that it can explain when and where stars formed? So we're fitting it to the actual data, but this model can explain, this very simple model, both the old and the young stellar populations. But it'd be cool if we could predict it, and so we should talk more about that.
Got it. Yeah, it looks like there are lots of hands up, so I yield the floor.
Yeah.
Steril, would you like to ask a question next?
Yeah, thanks for the nice talk. I had, so the picture you show really looks like it's a local bipolar outflow, or maybe at best a local ring. So I was wondering how much in galactic height can you actually trace it, and how much in azimuth? Because I would have thought a spherical shell probably isn't realistic for such an inhomogeneous medium. It should blow out vertically in a chimney, and it should be engulfing clouds and expanding asymmetrically in azimuth. And El-Badri's model are just 1D uniform spherical shells, which include evaporation but don't really include the 3D effect.
Yeah. So we know that the local bubble, if you actually, let me go back to a current picture. So there's still, so basically the model for the local bubble and its boundary is very well constrained near the galactic plane. So within about 100 parsecs, 50, 100 parsecs off the plane, there are still some very strong arguments about whether the local bubble is a galactic chimney. And so the dust models become much more uncertain at high latitude about whether it's actually closed or not, because there's much lower density. And so it's very unclear whether it breaks out of the disk. And so really the spherical shell expansion model that we're only fitting it to the dense gas. And so it's just, given the limited amount of data that we have on how the bubble's evolution evolves over time, like we're fitting this to like 30 clusters, there's no way for us to trace the gas unless it's formed in a dense cluster. And so we can't trace the low density gas at all. But it's the best approximation that we have given the data that's available.
I guess I was wondering, you stated there were 15 supernovae needed to power it, but that must be very dependent on assuming it's spherically symmetric in the amount of evaporation that's put into it.
Yeah, so basically the model that we're using, it's assuming there's a uniform ambient density, which we know is not true. We also know that there's spiral arms on either side of this structure. And so it's interacting with very dense gas on either side. And so you can see that most of the star formation is happening on the left and the right-hand side of the bubble, because there's existing structure there. And so I think there's probably a combination of enhancing and triggering star formation. So it's a very simplistic model, but it's the only one we have so far, given the data that's available. But it's definitely not spherical. I mean, it's 100% not spherical, but it's the model that we're using. But if there's another model that you like, I'm not sure what else we would be able to use other than a sphere, given that we only have constraints on its radius at like 10 epochs in time or something like
that. Costa, would you like to ask a question next?
Hi, Katherine. Thanks for the great talk. I had a couple of questions. One was, do we have any estimates on, say, the number of such bubbles that we expect in the neighborhood or like in the Milky Way? And like what observational data, or how do we like try to find these bubbles when they are like not very nearby? Like, do we trust the 3D dust map a few, say, kiloparsecs away? And another question I had was, is the North Polar Spur in any way related to the local bubble expansion? And another question that I just came up was, after Sterl asked this question, was that, is there any evidence of this early 15 supernova that we have in terms of, say, is there a neutron star remnant or something that we can point to that to say that this were the supernova which could have given rise to the local bubble?
Okay, so there's like four, so let me just like go through them. So can you just like, so the first question, I think I already forgot it. What was the first one?
Sorry. Yeah, the first was, is there any estimate on, say, the number of such bubbles we expect? Yeah.
Yeah, so you can get predictions from numerical simulations. And so I think there'd be on the order of like a dozen big bubbles in the solar neighborhoods within the nearest 500 parsecs. And a lot of them are like very famous, well-known bubbles. So bubbles like the Orion-Eridanus superbubble, Loop 1 is in there as well. There's the Perseus-Taurus superbubble. There's a superbubble near Vela in the south, and Cepheus as well. And so there's sort of superbubbles on all sides. And so in terms of your question of trying to figure out exactly where they are, and so if the superbubble is like a known superbubble, that's really helpful because we know sort of where to look. But the idea is that you have to correlate 3D and 2D data. So we have a model of the 3D dust as like an absence of material. But then we also know that if it's powered by supernovae, you should have signatures of supernova activity. So things like aluminum-26 as a supernova tracer, H alpha, soft X-rays. We look at all of that and try to correlate the 2D and the 3D. In terms of sort of how far out we can do this study, so right now we're really limited to the nearest 500 parsecs. So we just don't have the spatial resolution. So we can't do it sort of all across the galaxy, but we can extend this analysis sort of in the vicinity of the sun beyond 200 parsecs, which is what we've done for the local bubble, and sort of catalog all those bubbles. But I think with future Gaia data releases, we'll get better and better 3D dust maps. And so we'll be able to do this farther out. So hopefully we can go out to a kiloparsec, but we will see.
Okay,
and then the North Polar Spur, I think like the North Polar Spur and like Loop 1. So like I have to actually give Calstuff a whole ton of credit, since the only reason I ever looked at the local bubble was because he published a really amazing paper on a distance constraint to something called the North Polar Spur. And he found that the North Polar Spur sort of touches the local bubble on one side. So that's why I actually looked at it in the beginning. So everyone should check out Calstuff's paper. But yeah, we think that the North Polar Spur and Loop 1 are interacting in the direction of the Galactic Center. And so Gina actually has some really nice constraints on the Loop 1's distance, and they agree really well at high latitude, the surface of the two bubbles. Yeah. And then I think was that all the questions, hopefully?
Yeah, the last one was, is there any signature of, say, a neutron star or some source which could say that this are the specific 1514 supernova which happened?
Yeah, so the 15 supernovae you could only get from independently from the population synthesis modeling. So looking at the current stellar population of these two clusters and figuring out which stars are missing and must have already exploded. So the most recent supernova that went off was about 2 million years ago. And so we actually there is a radial pulsar that actually we think is associated with that most recent supernova explosion. This is from Neuhauser et al.'s work. But beyond maybe trying to find the neutron stars associated with this, there should be like no optically visible remnants or anything like that. But people are trying to associate the neutron stars and the runaway stars from these explosions with the UCL and LCC, which are the progenitor clusters. Yeah.
Okay, thanks a lot.
Mm-hmm.
Great, Gina?
Hi. So I find this super interesting, as you know, Katherine. What I'm really curious about is the systematics in the 3D dust extinction maps, because here you're using two different maps, right? And if I look at the paper by Like et al., the Lallemont map looks very different than the one that they made. And so I'm wondering, have you looked at how the bubble surface changes depending on the map that you use to define it?
Yeah, so it changes, and I think Vincent Pelgrim's paper also talks about this. So it changes depending on which dust map you use. It changes a lot at low densities, So at like high and low latitudes, it's very uncertain, but at high densities, it doesn't really change that much. It's pretty robust. And so one of the things that sort of gave us a lot of confidence is that we looked at, for instance, not just the local bubble is traced as an absence of stuff, so as like a low density region, but there have been other attempts from other studies to map it, like looking at sodium absorption lines and figuring out the extents, like when you sort of start to see the neutral shell and sodium absorption lines. And I can actually show that to you as well. Hold on a second. But the idea is that a lot of them, like essentially all of these measures agree. So how you trace the bubble via like polarization percentage of stars, like in front of and behind the shell, as an absence of like dust structure. So this is, for instance, let me see if I can find it. Yeah, so this is actually a map of the local bubble from sodium absorption. And so basically this black stuff is like a shell of neutral gas. And then basically there's no shell of neutral gas. So it's just a volume density of sodium 1. And then basically these little spines are star forming regions. This is from 2003, and it's based on basically 1,600 stars. We find that even in sort of this model for the local bubble from 20 years ago or 15 years ago, you still find star forming regions on the shell. And so we looked at basically every metric that we could, and then every metric that we looked at, like within the bounds of the errors of the various metrics, these star forming regions lie on the surface of the bubble. And so it's very strong agreement at like moderate density regimes. Yeah. Yep.
I see. And just to follow up on that, does the mass for the shell and the thickness change a lot with different maps?
The biggest uncertainty in the mass for the shell is not necessarily from one map to the other, but it's actually for how thick it is. There's a lot of uncertainty. Like it's really easy to find like the first sharp change in extinction about like when the first inner surface of the bubble is, but it's much harder to find the outer surface of the bubble. And so there's some pretty large range in the swept up mass based on the thickness of the shell and based on the different models. But that's sort of part of the reason why you get such a large, there's like such a broad distribution of the number of supernovae, because the swept up mass goes into that calculation. And it's uncertain by pretty large amounts, like 500,000 solar masses or something like that. So it's pretty significant.
Thanks.
Yeah. Mm-hmm.
Right. Mike, would you like to ask a question?
Yeah, so thanks for the nice talk. So I was wondering a bit more about what your thoughts are about the connection between the local bubble and these large filamentary structures. So in previous papers that you've written and written by your co-authors on this, you've shown quite convincingly that a lot of the nearby star forming regions are within these long filamentary structures, but these filaments continue beyond the local bubble, and there are other star forming regions within the filaments, like the North America Nebula or Cygnus X. And in the split, there's also the Aquila and Serpens regions. So I was wondering what your thoughts are about the connection between the two. Are these different models, or are these part of the same models? And can the formation of the bubble be related maybe to the formation of the filaments?
So you're talking, just to clarify, you're talking about the filaments like on like the 10th, like the 0.1 parsec scale filaments inside these clouds, or you're talking about like on large scales, the filamentary structure?
Yeah, the large scale filamentary structure that you talked about at the beginning, like the Radcliffe Wave and the split.
So the relationship between star formation in something like a spiral arm and star formation in these superbubbles?
Yeah. Mm-hmm. So I guess in the Radcliffe Wave, you've included Taurus as part of that, but also Orion, the North America Nebula, and Cygnus X.
Yeah. So the question is, so is your question, so let me actually, let me see if I can just show you really quick. So I don't know if I'm entirely going to answer your question. So I can't explain the North American Nebula at all, but I can explain, just bring up a map. Actually, let me just bring up my figure really quick, sorry. So let me turn on. So these are two sections of, this is the Radcliffe Wave, and this is the splits. And so just three things. So like so this is a local bubble, right? So we have one star in the star formation, the Radcliffe Wave on the local bubble. And then there's another super bubble right here. It's called the Perseus-Taurus Superbubble. So there's another one right here. Down here, this is Orion. This is the Orion-Eridanus superbubble, which is not shown, but there's a big ring of dust here in the Radcliffe Wave down here. And then people have argued that there's also another superbubble in Cepheus up here at about 300 parsecs. So at least everything that's on inside the spiral arm within 500 parsecs, it's all on the surface of a bubble, I would argue, or at least that's what I'm thinking. I'll have to actually read the paper to prove it. So yeah, so I don't know about the North American Nebula. I don't have any constraints, but I would estimate that a large fraction of the stuff that's in spiral arms and spurs, it's forming inside super bubbles inside these spiral arms and spurs. Yeah, I don't know if that's if I'm answering your question, but we can talk about it more offline. Okay.
Yeah, there was one paper by Eve Ostraker that related supernovas to the formation of bubbles, and
yeah, so I think related. Sorry, filaments to the formation. These filaments to the formation. I know where you have. Yeah, I think I know the paper that you're talking about. Yeah, so they have like the super bubbles form, and then you have the differential rotation, and then they also have like these like little spur-like features forming off the arm at the same time. Is that the one you're talking about? There's that one. Exactly. I know that paper. Yeah, so I don't have any thoughts on it right now, but we should talk more because I just haven't done any comparison with the two models. But I think we can start to do that. But we just had to sort of find the correlation first, and then we can sort of compare it with simulations. But I do know the simulations you're talking about.
Okay, great, thanks.
Yeah.
All right, I don't see any more raised hands, so let's thank Katherine again for a great talk. I will stop the recording, but you can stick around if you have some more questions. You have about 5 minutes left.